The next lesson in our trigonometry unit for Algebra 2 is this one. It's section 5.7, Solutions to Trigonometric Equations. And I will tell you, I'm not teaching you anything new in this lesson, but we are going to be pulling some things together in some new ways. You're going to be making some connections, and hopefully by the end of the lesson, you'll have a better idea, big picture of how some of this trigonometry stuff works together. So let's go back to when you first learned about trigonometry back in like freshman year. And I gave you statements like this: cosine theta, and maybe I didn't even use theta because we were new to trigonometry and it would have scared you. But if I told you cosine of some angle is 0.766, and I said, can you tell me what angle that is? Can you find theta? Okay, that's our goal here. You probably would have done this, right? You probably would have done an inverse cosine, and that would be absolutely correct. That would be a perfectly valid way to do this, because that's what the inverse trig functions do. So I would have typed in, and by the way, I should mention, I'm going to do this first problem in degrees. So I've got my mode set to degrees here, just because I think it's more intuitive for you. We could also do it in radians, okay? And we're going to talk in a minute about how to know when to use which one. But I'm going to use degrees. And I'm going to do inverse cosine of 0.766. And I end up with, I'm just going to call that 40 degrees. So my first kind of way that I could solve this is with an inverse cosine. And that's a realistic way to start one of these. Inverse cosine is 40 degrees. And back as those young, naive freshmen, we would have written that answer down and felt pretty good about ourselves and carried on with our day. Okay? And that answer's not wrong. Okay, the cosine of 40 degrees is 0.766. But now we know that there's another angle that would have the same cosine, that your calculator only gives you one of two possibilities. So if you think about the circle, we now know that if I draw a 40-degree angle here, the coordinates of this point would be 0.766 for that cosine. And then there's going to be some sine value too. I don't know what it is. Doesn't matter to me. Okay. But that cosine value, that 0.766, is really representing like the x value, right? It's really saying how far out along the x-axis that point is. And there's another point that is that same distance away that would have that same x value, and that's going to be down here. Okay. So whatever angle this is also going to have a cosine of 0.766. And then it's going to have a sine value that's the opposite of the one that's up above it, right? Okay. So to find what this angle would be, and I don't want to just call it negative 40. I know we talked about how this is positive 40 and this is negative 40, and that's true. But if I want to talk about it in terms of like from 0 to 360, and I want to know what would this angle be called if I went around and found it this way, what I'm going to do is I'm going to take that 360 and subtract the 40 degrees, and I'm going to find that a 320 degree angle should have the same cosine. So both of these answers are valid. Okay? And just to verify that, here's the cosine of 40. Whoops. 0.766, and obviously that's rounded a little bit. And then if I were to do the cosine of 320, I also get 0.766, okay? So now we are advanced enough in our trigonometric knowledge to know that there's two correct answers to this equation, okay? And technically I have to give both of them if I want to be 100% accurate, okay? But wait a second. What if I do the cosine of 400 degrees? Look at that, cosine of 400. Or what if I do the cosine of 680 degrees? Look at that. Okay, so what's happening there? Remember that these are just one stop on the unit circle, right? This is part of these two angles that we just marked here are part of the first rotation. But what if I kept going? Okay, what if I stood here and then wrapped all the way around again and landed back on that point? That angle, by the way, that would be 400 degrees, because that would be 40 degrees plus another 360. That's where the 400 came from. Okay, I could keep going around and around and around by 360 as many times as I want. So really, I could come up with an infinite number of angles, both positive and negative, that have a cosine of 0.766. And so that's going to be a lot harder to list out, right? I mean, we could start listing the ones that I came up with, but here's an easier way to say this. I'm going to take that 40-degree answer and I'm going to say, hey, we could take that 40 degrees and add 360 to it as many times as we want. And by putting that n there, that means I could add it 1 time, I could add it 2 times, I could add it 5 times, I could add it 10 times. Okay, so just for reference here, if I took, I'm getting really bad glare today, sorry. If I took 40 and I added 365 times, I would get 1,840. If I did cosine of 1840, I would bet it's going to be 0.766, okay? So that's what this answer is saying, that if we want to really include every possibility, it's an infinite number, but it goes around by this amount every time. And then I have to say the same thing about this point down here, because me going around by 360 from this point is not going to include those red ones. So I could say 40 plus 360n and 320 plus 360n. Okay, so there's sort of 3 different ways to answer this question, and I don't really want to say ways because you're always going to start out this way. Okay, you're always going to start with that inverse cosine, but there's layers to it, right? There's, do we only care about that one answer that our calculator gives us? Do we care about, somewhere on the circle and knowing that there's 2 possibilities? Or do we care about the fact that we could go around the circle forever and ever and have an infinite number of possibilities? Okay, and that's really what we're going to be talking about today. By the way, I meant to mention this because we could also go negative angles, right? Remember we said we were going to call this 320 because we wanted to use a positive angle. But what if I had called it negative 40? Okay, that would have been okay because cosine of negative 40 is also 0.766, okay? That's covered here because if I had called this, let's see, if this had been, how do I want to do this? If I had taken this and subtracted, so if I had made n negative 1, if I did this, 320 plus 360 times negative 1, okay, that's going to get me that negative 40. So the negative angles are included here just by letting the n be a negative value, okay? So these 2 really include all of the possibilities. It's an infinite number of possibilities. This right here, by the way, just so you know, when I write my answer like this is what's called a general solution. So anytime you hear me make reference to a general solution, really all you're going to do is solve the equation like you would in these first 2 steps and tack on a 360n. Or if you're working in radians, it might be a 2 pi times n, and you're going to see that down here in the periodicity theorem. Try saying that 10 times fast. But okay, so all this theorem is saying is that if I have an angle and I add 2 pi to it n times, which is kind of the same idea as adding 360 to it n times, the sign value is going to stay the same, right? So if I stand on this point and I wrap around by 2 pi or by 360, depending on which method I'm using, the sine and the cosine are going to stay the same. Notice that tangent technically has a pi n instead of a 2 pi n. The reason for that, and you'll see that when we start talking about tangent, but I wouldn't stress about that too much. Remember that tangents are the same in the first quadrant and the third quadrant. So actually, if I only wrap around by like 180 degrees, I can find another angle that has the same tangent, okay? And so really, instead of having to write 2 separate things here when you're working with tangent, you can just write 1 and have it jump by 180. So 180 would include this one, another 180 would put you back here, 180 is going to take you back down there again. Like I said, if we do one that involves tangent, I'll show you that, but I wouldn't stress about that too much. Okay, so when you solve one of these equations, it'll always give you a domain that you're working on. And the domain that it tells you refers to which one of these 3 bullet points are you using? How far down in the process are you having to go? Okay, and this wording might not make a whole lot of sense, but it really relates back to those 3 bullets I did up here. Restricted domain of the inverse function. Essentially, this is what your calculator gives you for an inverse trig value. Okay, so that's that. That's one answer. Okay, so that first bullet point we did when we just typed in an inverse cosine, technically that was the restricted domain of the inverse function, meaning what does your calculator say the answer is? That whole restricted domain thing is just talking about the fact that where is your calculator going to pull its numbers from? Typically it's this first quadrant, okay? Depending on the value you type in, it may pull from either the second quadrant or this quadrant down here, but it's only going to give you one answer. An interval equivalent to the period of the function. That one's really not going to make sense to you because this year in particular, we haven't talked about the graphs of these functions yet. So I don't know if you're familiar with this concept of the period of the function, but really this is one time around the circle. One revolution around the unit circle. A lot of these are going to be in terms of pi, okay, in terms of radians. So when I'm talking about this interval, I'm really saying between 0 and 2 pi, or between 0 and 360 if I was living in radian land. So when you see me write something like this, give me all possible values between 0 and 2 pi, this is where I'm looking for two possible answers. Because if I'm just living on one time around the circle, there were two answers, like in that second bullet point we did up there. And then if I want to know all real numbers, which is the same thing as asking for a general solution, that's where I want you to somehow list off all the possibilities. And we're going to do that by adding 2 pi n or 360 n, depending on if you're in radians or degrees. Okay, and this is an infinite number of solution. Infinite, sorry, I can't speak and spell at the same time. An infinite number of answers, okay? But they're periodic, which means they repeat, and that's what lets us get away with generalizing this way, okay? So if I only ask you for a single answer, that's where you're just going to type it in from your calculator. If I ask you for this, which I will be honest with you, this is probably the most common thing you're going to see. You are going to type it into your calculator, get the one answer, and then figure out where on the circle the other answer comes from. By the way, I should point out this example we did together. We subtracted from 360 because we were working with cosine, right? And the cosine is the same here and here. If I had been working with sine, remember the sines are the same here and here. Okay, so I wouldn't have subtracted from 360, I would have done something else. And so you really have to be familiar with that stuff we talked about in 4.4 about when are the cosines the same, when are the sines the same, that kind of thing. Okay, and then general solution is anytime I'm circling random things here, but general solution is where I'm tacking this onto my two answers. Okay, so I'm finding my two answers and then I'm doing this to it. Okay. Okay, let's try some of these because that was a lot of talking before we actually started working through any of these problems. So here's another cosine one. Okay, consider this equation, cosine theta equals negative 0.36. Find all solutions such that theta is between 0 and pi. Notice that's only talking about the top half of the circle. So if we think back to how cosine works, this interval right here refers to the top half of the circle. As far as cosine goes, that's only going to be one possible answer, right? Because the cosines are the same above and below the x-axis. Cosines are the same top and bottom. So if I'm only focused on the top, that means that I'm only going to have one answer here. Okay, that's the one from my calculator. Just so I can have a visual, if my cosine is negative 0.36, that means my x value is negative 0.36. And if I'm only looking at the top half of the circle, I'm probably looking at an angle about here. Okay. Now, the fact that they gave this to me with a pi in it tells me my calculator needs to be set in radians. But I am just going to do decimals for radians here. I'm not going to worry about converting back to values of pi. So in my calculator, I'm going to change my settings back to radians. And I'm going to do second cosine negative 0.36. Okay. And I get 1.94. And I know that's hard to make sense of because we're so used to dealing with radians that have pi in them. Really, this is something times pi. But if you think about it, if this is pi, that means this is roughly equivalent to 3.14 in terms of actual numbers. So having this be about equal to 2 makes sense. It's about 2/3 of the way to 1 whole pi. Okay? So now when I jump to this, such that theta is between 0 and 2 pi, now, so the first question just had me looking at the top half of the circle, which is why I only did this one angle here. Now I want to look at the entire circle, right? I want to look at from 0 to 2 pi. So now I have to think about where do I have a cosine value that would be the same? Cosines are the same above and below. So now I need to find this angle. If I know that this is 1.94, the question is, how do I get to this? Okay, this is what I'm trying to find. Whoops, that meant to be a question mark. All right, so we know that we're going backwards from 2 pi, and we're going backwards by 1.94. So to get my answer, I'm going to do 2 pi minus 1.94, and I end up with, and I'm literally typing that into my calculator because I don't have a pi value to work with. So 2 pi minus 1.94 is 4.34. So the way I would answer this question, because it wants all solutions, I would say theta equals 1.94 or theta equals 4.34. Okay, either one of those would be correct. And if you wanted to check, let's type in cosine of 1.94 and cosine of 4.34. And you'll notice you get that same, I must have rounded differently. They came out a little bit off here, but I think I must have just rounded this decimal differently than I did the 1.94. Okay, when you round these numbers, because they're irrational, it is going to make some minor differences, but they are both negative 0.36. Okay. Okay, illustrate your answers on a graph. I kind of did that already. That's what this is. All right, so I showed where my two answers would be located. This one is 1.94. This one, if I was measuring going around this way, this would be 4.34 here. Okay, it's negative 1.94, but positive 4.34. So this is up above. And then general solution. The general solution is really the easiest part. Okay, for the general solution, all I'm going to do is take my two answers and show that I could go around again and again and again. And so I'm going to say plus 2 pi n and then 4.34 plus 2 pi n. Okay, that's my general solution. General solution, you just tack this onto your answer and leave it alone. Okay. Let's look at one where we have to do some actual solving here. Notice in this one, I've got some numbers I have to clear out of the way. So I have 2 times sine theta plus 3 equals 4.414. My goal here, before I start, is to get to a place where I have sine theta equals something. So I can start it like all the other problems. So I'm going to start by just doing some regular equation solving. I'm going to subtract 3 on each side. Okay, and so that leaves me with 2 sine theta equals 1.414. And then I'm going to divide by 2. Okay, so just doing some regular algebra here. And I end up with sine theta equals, I think it's 0.707, but let's just make sure. Sine theta equals 0.707. Okay, so the first solution is going to come from doing an inverse sine. And I know I'm working in radians because my interval is given in radians. So inverse sine 0.707. Okay, and I get 0.785. Now, we need to think about where that second solution would come from. Okay, so let me get rid of this guy quick so I can draw a circle. Even when it doesn't tell me to draw a circle, I usually do. Okay, so if you're having a hard time visualizing where this is in terms of radians, I'm with you. I don't totally know where that's at, but I can think about where my sine value would be 0.707 because my sine is along my y-axis. And remember, this is 1. So 0.7 would be like here. Okay, and so this first answer that I came up with would be this angle here. And so this is 0.785 in terms of radians. Well, when I'm living in sine land, when I'm talking about the sine values, my other angle that would have the same sine is over on the left side of the graph. Okay, and so I need to know what this angle is. With sine, we're backtracking from pi. So I want to go from pi backwards by that 0.785, which is my angle value. Okay, so to find what that angle would be, I'm going to do pi minus 0.785. And I'm actually going to type that in. So pi minus 0.785. And we end up with 357. And these two numbers would be my two solutions that live in this range, right? Between 0 and 2 pi. These are my two values that are in that range. And again, if you were to do the sine of 0.785 and the sine of 2.357, you should end up with, and again, we rounded a little bit, but you should end up with a sine that is 0.707, okay, which is close enough here. And we could go all the way back to check this stuff, but I feel pretty confident that I subtracted by 3 and divided by 2 correctly, so I'm not going to do that. Okay, general solution. Remember, that's the easy part. I'm just going to take my two answers and tack on 2 pi n to show that I can go around and around the circle as many times as I want to. And then I can also do that starting at the 2.357. Those are my general solutions. That includes all rotations of the circle. Okay, in example 3 here, I'm going to do this in a way that's maybe more familiar to you, at least as of recently, because I see that this is written as a nice happy square root here. I'm going to try to leave it that way. I'm not going to dive into decimal land here. All I'm going to do is I'm going to divide by 3. And so then look at what I get. I get tangent of theta equals square root of 3 over 3. So here's the thing. I could type in inverse tangent of square root of 3 over 3, just like I did up here. Okay, and that's a perfectly fine way to do this. I didn't say that you had to do this with exact values, but I recognize this. This is from my unit circle, right? And so if I can think about where on my unit circle that tangent occurs, I can get to my answer without even having to use my calculator. Okay, I know that tangent of theta is square root of 3 over 3 at, I almost said 30 degrees, but we're living in radians, so this would be pi over 6. So at pi over 6, I recognize that tangent. Okay, so I can say, I know for sure that the tangent is square root of 3 over 3 when theta is pi over 6. Okay, well, where else would it be square root of 3 over 3? Remember, the tangents are the same down here in this quadrant. Okay, these two tangents are exactly the same. And so I know what this angle is, which this one is 6 pi over 6. So this would be 7 pi over 6. I would get the exact same value. So theta equals 7 pi over 6. So sometimes when there are values you recognize from the unit circle, it's easier than even relying on your calculator. Now let me show you what would have happened if we had done that with our calculator. I could do inverse tan and then type in square root of 3 divided by 3. Okay, do make sure you close that parenthesis there. And I get this crazy number. That's equivalent to pi divided by 6. Okay. And if I had been working with tangent, I know that the tangent value is always the same when I take pi and add theta to it. So remember we said that here our theta was pi over 6. Okay. So to get this other angle, really what I did was I took 1 pi and I added that pi over 6. to get 7 pi over 6. So if I took, let's see, I'm going to go back to that value we got from our calculator. I'm just trying to replicate how we did it before. I got that one tangent value. And then if I do pi plus that number, I get 3.66. That number there is equivalent to 7 pi over 6. And if I wanted to check that and make sure, I can do that. Okay. And notice that if I do tangent of that number, I get this 0.577. That's equivalent to the square root of 3 over 3. Okay. So really, everything I just did is the same as had you done this in your calculator. I like it better when these are nice exact values that I recognize from my unit circle, because then I can just pull the numbers right off of my circle and I don't have to rely on my calculator so much. But in something like this one where it gave you these decimals, or if you're working with non-perfect, exact values, this is the way you'll go. Okay, so you'll use the inverse functions on your calculator to get your first answer that gets you started. Then you think about where the answer would be the same, and that's going to depend on whether you're using sine, cosine, or tangent. Just a quick thing you might want to jot down. Remember that if you're looking for where the sine is the same, it's always going to be over here in the second quadrant. If you're looking for where the cosine is the same, it's always going to be down here. This is assuming your angle starts up here, okay? And then the tangent is always the same down here on a diagonal, okay? So you get to this by doing pi minus, right? That's for sine. You get to that cosine value by either taking the negative of the angle measure or doing 2 pi minus theta. And then the tangent value is always pi plus theta. And that's what we learned back in lesson 4.4. Okay, let's jot this. It's here, but this is really pi minus theta for sine. Okay, so give a few of these a try. And I do know that some of that sounds confusing. It really is important that you have a really good handle on how things work as you move your way around the unit circle. The better you are with that, the more sense this will make. But after you do a few of these, I think you'll be in better shape. I think the other thing that's hard about this lesson is there's a lot of places where you're getting these radian values that are in decimal form, and those aren't as intuitive. It's hard for you to picture where that would be on the circle, as opposed to if I'm talking about, 3 pi over 4 or something like that. But trust yourself, trust your math. You can always check the ways that I was showing you on the calculator to make sure the values are the same, that kind of thing. Okay, that's it for whatever lesson this was, 5-7. I hope you guys have a great day, and we'll talk about this next time I see you in class.